Welcome to the presentation on the Recognizer project, an exploration into the power of neural networks through the practical application of recognizing handwritten digits. Today, we'll discuss how this project not only enhances our understanding of machine learning, but also provides a user-friendly platform for digit recognition. The project proposal describes application that will allow users to upload images with handwritten digits, recognize and output the written numbers. User interface. With functionality to train model, select images for recognition, execute recognition, output results, functionality. Using dataset train model with specified parameters, save model on disk. Recognize numbers in provided images using saved model. This project is centered around artificial intelligence, specifically using a type of machine learning called neural networks to perform image recognition. Neural networks are designed to mimic the human brain and are particularly effective in recognizing patterns from complex data, such as images. This task is commonly considered as a hello world in machine learning. The recognizer is implemented using Python 3.10 and several libraries like NumPy for numerical computations, Pandas for data manipulation, PySide2 for the graphical user interface, and PIL for image processing. The UI provides user with tools to extend original dataset, train models, switch between models, and recognize digits from test MNIST dataset or custom images. I utilized the MNIST dataset, which contains 42,000 training images. The data files train.csv and test.csv contains grayscale images of hand-drawn digits from 0 through 9. Each image is grayscale and 28x8 pixels. The data for every number stored in CSV table as rows. The first columns represents label, actual number, and other 784 columns stores float values for each pixel of the image. The data augmentation technique, such as rotation, was applied to source data set to challenge the model with real-world scenarios. Application loops through each line in the CSV file, convert numbers to PIL image, rotate image 90, 180, 270 degrees, convert image back to array of floats, and record this data to the new CSV file. The Recognizer application has Recognizer class that uses a two-layer neural network for digit recognition. The network is trained using gradient descent, a common optimization algorithm in machine learning. The Recognizer class is the main class in the system that encapsulates the functionality of the neural network model. It is responsible for training the model, making predictions, and saving and loading the model parameters. Recognizer UI allows user to train and retrain source and extended models, extend data, display images from train.csv, dataset for validation, and finally recognize digits. In this project, we've utilized several fundamental AI and machine learning concepts to develop and refine our neural network model for digit recognition. First, we employed a two-layer neural network, where each neuron-like node connects via synapses, performing complex computations. This structure allows the network to process input data effectively, making predictions based on learned patterns. To optimize our network, we implemented gradient descent, a powerful algorithm that iteratively adjusts the network's parameters to minimize the loss function, which in our case is the cross-entropy loss function. This particular loss function evaluates the accuracy of the output by comparing the predicted probabilities against the actual class labels, ensuring our model's predictions are as accurate as possible. The model's ability to handle complex patterns is significantly enhanced by the use of activation functions. We use the rectified linear unit, or ReLU, for the hidden layers to introduce nonlinearity, enabling the model to learn more complex patterns. For the output layer, the softmax function converts the outputs into a probability distribution over predicted classes, which is essential for multi-class classification like digit recognition. Furthermore, to manage categorical data effectively, we utilized one-hot encoding to represent digit labels. This encoding transforms categorical labels into binary vectors, which are easier for the model to process during training. The processes of forward and backward propagation are central to our model's training. Forward propagation computes the output given the current parameters, while backward propagation adjusts these parameters by calculating the gradients of the loss function and running these calculations back through the model to update the weights and biases. To enhance computational efficiency, particularly with large data sets like MNIST, we implemented a vectorized approach. This method uses matrix and vector operations to perform calculations across all training examples simultaneously, rather than looping through each example individually. This significantly speeds up the training process and improves the scalability of our model. And reflecting on the development of the Recognizer project, several key lessons were learned that not only enhanced our understanding of machine learning, but also improved our skills in practical application development. First, the importance of data pre-processing was highlighted through our approach to normalize the input image's pixel values between 0 and 1. This normalization is crucial as it ensures that all input features have a similar scale, significantly aiding in the model's faster convergence during training. Regarding model training and evaluation, using the MNIST dataset allowed for a structured training approach, while evaluating the model on a separate test set helped in assessing its performance accurately. This practice is vital to avoid overfitting and to ensure that the model provides an unbiased estimate of its capabilities on new, unseen data. A major efficiency gain was realized through the ability to save and load trained models. In this project, the trained weights and biases of the neural network were saved to CSV files. This feature allows the model to be reloaded and utilized immediately without the need for retraining, saving both time and computational resources. User interface design also played a critical role in this project. By developing a user-friendly graphical interface using PySide 2, the application became accessible to non-expert users, allowing them to interact with the system intuitively. This aspect of software design is crucial in bridging the gap between complex machine learning algorithms and end-user usability. Throughout the project, debugging and error handling were continuous focuses. Addressing various bugs and potential issues with data input and matrix operations was crucial for ensuring the stability and reliability of the application. These activities underscore the importance of rigorous testing and quality assurance in software development. Performance optimization was another key area of learning, particularly the use of vectorized implementations for the neural network's forward and backward propagation steps. These implementations are significantly faster than traditional loop-based processing, especially critical when dealing with large datasets or complex models. Lastly, building a neural network from scratch deepened our understanding of essential AI concepts such as gradient descent, activation functions, and one-hot encoding. It provided a hands-on experience in understanding how neural networks operate, from the intricacies of forward and backward propagation to the nuances of tuning and optimizing a model for better performance. Each of these lessons not only contributed to the success of the Recognizer project, but also enriched our overall grasp of implementing and managing AI and machine learning applications effectively. Throughout the project, I faced several challenges, including managing the increased complexity of data due to the rotations, ensuring the model could generalize from the training to real-world data effectively, and optimizing the training parameters, such as the learning rate and number of iterations, to refine our model's performance. As we look to the future of the Recognizer project, several enhancements stand out to further elevate its performance and user experience. First, we plan to extend the dataset by incorporating scaled images. Currently, our model handles rotations, but adding non-proportional scaling could significantly broaden its recognition capabilities. To address more complex patterns effectively, we're considering adding additional hidden layers to our neural network. This could potentially enhance its ability to decode more intricate and subtle variations in handwriting. Experimenting with different activation functions beyond the current ReLU and softmax could offer improvements in model accuracy and processing speeds. Activation functions like leaky ReLU or ELU might provide better performance, especially in handling nonlinear data. Hyperparameter tuning is another area of focus. By optimizing the learning rate and the number of training iterations through techniques such as grid search or random search, we can achieve more precise model tuning, enhancing both efficiency and effectiveness. Implementing regularization techniques like L1 and L2 will be crucial to prevent overfitting, especially as our model complexity increases. This will help in improving the model's generalization ability across unseen data. Improvements to the user interface are also on the agenda. We aim to provide users with the ability to adjust learning parameters directly through the interface and enhance visual feedback during the training process, making the system more interactive and user-friendly. Additionally, introducing a control mechanism for data augmentation will allow us to manage the dataset's complexity more effectively, ensuring that our model is trained on balanced and representative data without being overwhelmed by too many variations. Lastly, we're contemplating a more robust model architecture that could include deeper networks or the integration of convolutional layers, which are particularly effective in image recognition tasks. This enhancement would be aimed at better capturing spatial hierarchies and features in handwritten digits. Each of these improvements is geared towards making the recognizer not only more accurate and efficient, but also more adaptable and easy to use, pushing the boundaries of what our application can achieve in the field of digital image processing. In conclusion, while the Recognizer project did not fully meet the initial expectations due to lower accuracy with the augmented dataset, it provided valuable insights into the challenges and potentials of neural networks in image recognition. The results deviated from the initial proposal, especially in terms of model performance with rotated images, prompting a re-evaluation of some of the initial assumptions and strategies. This project serves as a bridge between theoretical knowledge and practical application, laying a solid foundation for further exploration into advanced machine learning techniques. It demonstrates the challenges and rewards of applying neural networks to real-world problems.